Okay, we're on. Right, question 4, game theory question. Again, really, really important that we read the questions carefully. Rowan and Colin are playing a game of scissors, paper, rock. Surely it's rock, paper, scissors. Isn't that what we call it? Yeah. Okay. And each round of this game, each player chooses... Well, you know how to play the game. The rules of the game are that... Yeah, okay. But they're given points for different things. Right. Shh. They're given points for different things. According to whether they win, draw or lose. And these are the points won by Rowan and the points won by Colin. Right. It gives the following payoff tables. Use an example to show that this is not a zero-sum game. So we just need an example where they are getting different scores in the two things. There are a number of examples in the table. The one that I spotted, the one that I wrote about, which I think quite a few of you did as well, was Rowan choosing scissors and Colin choosing paper. That was the example because that is that option there. Okay? Rowan chooses scissors, Colin chooses paper. So Rowan would win 1 point. Have I said that right? Rowan, scissors, and Colin chooses paper. Rowan gains 1 point, and Colin loses 2. Okay, that's the way it works. It's +1 for Rowan and -2 for Colin. Now, I'll be really careful about this. Quite a lot of you at this point did something very similar to that and said 1 is not equal to -2. That's a true statement, well done. But unfortunately, it's not a particularly helpful statement. If this had been a zero-sum game, what would you have written at that point?
-2 + 1 is not equal to 0.
Yeah, you would have said somehow that the sum gives a 0. You wouldn't have written 2 equals -2, because that's not true either. 2 doesn't equal -2. That's not the point of a zero-sum game. It's not that one score is the same as the other. We're not showing that these are not equal. That doesn't actually prove anything. The thing that proves something is that if you add the scores together, it should be 0. So if we do 1 plus -2, that should equal to 0 if it's a zero-sum game, and it doesn't. And that's what you needed to show that it wasn't a zero-sum game. So quite a lot of you had the right point, kind of in the right direction with it, but just didn't quite get across the zero-sumness thing at the end. Then it says, write down the minimum number of points that Rowan can win using each strategy. This was quite a straightforward thing. Looking at this, using each strategy, what's the worst thing that could happen for Rowan? It's -1, it's -2, it's -2. And we know that playing safe means that you minimise the number of points that... hence find the strategy that maximises the minimum number of points. You want to make things as good as possible here. So he's going to choose scissors, isn't he? Because that guarantees that his minimum score, his minimum number of points, is -1 rather than -2 for the others. Then it starts to feel like it's getting a little bit more complicated, but it's not really. We're told Rowan decides to use random numbers to choose between the 3 strategies: scissors with P, paper with Q, and rock with 1 - P - Q. Find and simplify in terms of P and Q expressions for the expected number. So, okay, we're looking at what happens in each of the cases. If Colin chooses scissors, then what happens to Rowan? If Colin chooses scissors, then Rowan wins 0, -2 and 2. Okay, does that make sense? So Colin chooses scissors. Are you with us, Tom?
Yeah.
So if Colin chooses scissors, it's 0 for P, 0p, -2 times Q, plus 2 times the other bit. So we're going to write here Rowan wins (0p) minus 2 times q plus 2 times 1 minus p minus q. And if you collect together like terms within that, it gives you 2 minus 2p, and then that's minus 4q. So that's our answer for that one. The next thing to work out is the same thing with Colin chooses paper. And I'm not going to do another row for that, I'm just going to write, I'm going to write it under here. That's 1, 0, minus 2, so that's 1p plus 0q minus 2 times 1 minus p minus q. Work out the equation, and that gives us 2 plus 3p, is that plus 3p? Minus 2q. That's that equation sorted out. And the last one, if Colin chooses rock, then that is minus 120, so that's minus p plus 2q. And actually we don't need to simplify that, plus 0 times the other stuff. So that's all we get for that answer. Those are the 3 equations we get for that. Happy with that? And it was 3 marks, so I think it was pretty much 1 for each. And I missed a mark.
On the thing, it's not 2 plus 3p minus 2q.
It's
Supposed to mean Emily got 3p plus 2q minus.
oh, it's minus 2. This is a minus 2.
And
Yeah,
it's
it's
a
minus
plus
2
2q.
times 1. And then it would be a plus 2q. That would be right, wouldn't it? Yes. Thank you. I'd missed the minus sign there, hadn't I? Right, is that better? Minus 2 plus 3p plus 2q. There we go. Right, part 4 said Rowan wants his expected winnings to be the same for all 3 of Colin's possible choices. Right. He wants the expected winnings to be the same. This is heading towards simultaneous equations. It's a bit of an unusual thing, but he wants his winnings to be the same. Let's call his winnings, what should we call it? V, for the value of the game. So that means all 3 of these equations are now equal to V. So V is 2 minus 2p minus 4q. V is minus 2 plus 3p plus 2q. And V is minus p plus 2q. He wants the value of the game to himself to be the same in all 3 cases. We have 3 equations in 3 unknowns. So we need to solve these equations simultaneously. Let's call them equations 1, 2 and 3. What could we do? Well, we could eliminate V quite easily because they're all in terms of V. So if I equate equations 1 and 2, to get rid of V, that's 2 minus 2p minus 4q is minus 2 plus 3p plus 2q. If I sort this out, collect like terms together, what have I got? I've got 4 equals 5p plus 6q. So that gives me another equation. If I look at equations 1 and 3, that gives me 2 minus 2p minus 4q is minus p plus 2q. So this equation gives me 2 equals p plus 6q. Brilliant. Call that equation 4 and that equation 5. This just keeps on getting better because I've got the same coefficient of q in both equations. So if I subtract these equations, if I do equation 4, take away equation 5, I get 2 is 4p, which means that p is a half. Got the value of p as being a half. If I sub that back in to one of the 2 equations, 2 equals a half plus 6p, so 6p is 3 over 2, so p is 3 over 12, that's a quarter. That was a cube, sorry, that I've talked about there. I've written it as p each time, but it's a cube. that better. That's that equation there that I've subbed it back into. And the last bit is easy, because these add up to 1. So if that's a half and that's a quarter, the other one must be a quarter as well. And they are my probabilities. It was just solving the simultaneous equations at the end of it. The trick was noticing that you needed to have them all being equal to the same amount. That's what it said in the question. When it said they're all equal, he wants to have the expected weighting to be the same for all 3 of the cases. There we go. And that's maths.